Welcome to the deep dive. Today, we're plunging into something that you might remember from your school days, quadratic equations.
Oh, hi.
Stick with us, though, because we're not just, dusting off old formulas.
Right.
We're exploring how this seemingly abstract piece of math just pops up in the real world,
Yeah, it does.
helping us crack some surprisingly practical problems.
Exactly. When you hear quadratic equation,
Mhm.
you might picture, well, pages filled with algebraic steps, right?
Yeah.
But at its core, it's really a pretty simple equation
Mm.
where the highest power of a variable is 2. Think of something involving x squared.
Okay.
What's truly remarkable, I think, is how many different kinds of situations can be modeled and solved using this basic mathematical structure.
Absolutely. And for this deep dive, we've got a great set of examples, almost like little puzzles waiting to be solved.
Mm-hmm.
Our mission today is to uncover how these quadratic equations are, like the hidden key to figuring out everyday mysteries. We're talking about finding secret numbers, understanding how time and effort play out in work scenarios, unraveling geometry, even making sense of buying and selling.
Lots of ground to cover.
Totally. Ever wonder how knowing just a couple of things about two unknown numbers can actually let you figure out exactly what they are?
Right.
Or how, say, a small change in speed can have a big impact on your travel time?
Yeah, those nonlinear effects.
These are exactly the kinds of questions we're tackling today.
And as we explore these examples, you should keep in mind the fundamental process. It's really about taking a real-world situation,
Okay.
translating it into the precise language of algebra, specifically, a quadratic equation,
Right.
and then using the mathematical tools to find the solutions. It's a really powerful method.
Okay, let's dive into our first category then. Problems based on numbers.
Right.
So imagine trying to find two natural numbers. We know that one is 3 more than the other.
Okay.
And if you square both of them and add those squares together, you get 117. How do you find these mystery numbers?
Okay, this is a perfect example of how we turn words into algebra.
Uh-huh.
If we call one of the numbers, say, x,
Right.
then the other one, since it's 3 more, must be x plus 3/5. Simple enough.
Yep.
The problem tells us the sum of their squares is 117. So we can write that as $6 plus dux x plus 3 to go 117 is having a problem.
I see.
Notice how the word squares in the problem leads directly to the 6/221 and sx plus 322. That's what makes it quadratic.
Right. And when you work through the algebra, expand that x plus 3 combine terms, move everything to one side, you end up with a quadratic equation. X by $1 plus 3 by 54 equals always the others.
Exactly. And now this particular one can be factored. It factors into x plus 9 by 6 equals dilly,
Okay.
which gives us 2 possible values for x minus 9 and positive 6.
Right. 2 possibilities.
But here's where the context of the problem is key.
Uh-oh.
We're looking for natural numbers, positive whole numbers.
All right, 1, 2, 3.
Exactly. Squaring works for negatives, sure, that's why nan and 9 popped up. But we need natural numbers.
Okay.
So we discard the nan and 9. That leaves us with x is 6. And if one number is 6,
The other one is x plus 3, so
there
9.
you go, 6 and 9. That's the aha moment when the algebra gives you the answer.
Okay, let's try another number puzzle. Bit different.
Sure.
This time, we have a whole number. 5 times this number equals 3 less than twice its square.
Okay, 5 times the number equals 3 less than twice its square. Let's translate again.
Yep.
Let the number be x. 5 times the number is just 5 by x.
Right.
Twice its square is 2 by 2, 2 less. And 3 less than that is 2 by 2, $2.
Okay.
So the equation is $5 equals 2 by $2, 323.
Okay.
So the equation is $5x equals a zealer. Okay, 2 by 2, 5 by 3 equals now.
Okay. 2 by 2,
Yeah.
5 by 3 equals dollars. Okay.
Yeah.
2 by 2, 5 by 3 equals no dollars. And if we factor that,
Uh-huh.
we get 6 by 3, 2x plus 1 equals dollars.
Right.
Which gives us 2 possible values for x3 and minus 1/2.
Exactly. And again, we check the problem's conditions.
It's at a whole number.
Right, which usually means non-negative integers, 0, 1, 2, 3.
So minus 1/2 is definitely out.
Definitely out. Which leaves us with xly 3 as the only valid solution.
Okay, simple enough when you follow the steps. Here's one that sounds a bit more involved, though.
Let's hear it.
We have two natural numbers. They add up to 8.
Okay, sum is 8.
And the difference of their reciprocals is 2 divided by 15.
Ah, reciprocal. So fractions are involved.
Yep. What are the numbers?
Okay, same principle. Let one number be x.
Uh-huh.
Since their sum is 8, the other must be 8x.
Makes sense.
Now, the difference of their reciprocals, that means frac 1x dennis to pico.
Right.
And we're told that equals 215. So frac 1x track 15.
Okay. And having x in the denominator often leads to a quadratic, right?
Very often, yeah.
Yeah.
When you go to solve
We
this...
find a common denominator, combine things, cross-multiply.
Exactly. All that algebraic legwork. It eventually leads you to the quadratic equation 6 by 2, 23x plus 60 equals the Lauer.
6 by 2, 23x plus 60 equals 60.
And that one factors too. It becomes 6 by 20 on then by 3 over.
So potential solutions are x, 20, and x equals 3.
Potential solutions, yes. But we have to check them against the original conditions again.
The sum has to be 8.
Right. If x were 20, the other number would be 8 minus 20, which is minus 12.
Not a natural number.
Nope. So we discard x equals 20.
Which leaves x is 3.
Exactly. And if x is 3, the other number is 8 minus 3, which is 5.
So the numbers are 3 and 5.
That's it. They add to 8, and the difference of their reciprocals, 13 minus 15. Let's see. 515 minus 315 is 215. Checks out.
It's really fascinating how these, well, seemingly straightforward conditions just naturally lead to these quadratic equations.
That is.
And looking at the examples like in exercise 6a from our source material, there's quite a variety just in number problems. Consecutive integers, sums of squares again, reciprocals like we just did, dividing numbers.
Yeah, it shows the versatility. The core thing is that the problem describes the relationship where the unknown quantity gets multiplied by itself, or interacts in a way that algebraically results in that $6 term.
Right, that's the key. Okay, let's shift gears a bit. Let's talk about problems based on time and work.
Ah, yes. Rate problems.
Here's a scenario. Person A can do a job in 6 hours less than person B.
Okay, A is faster.
If they work together, they finish the job in 13 hours and 20 minutes.
Right.
The question is, how long would it take person B to do the job all by himself?
Okay, these rely on the idea of work rate. How much of the job gets done per hour?
Right.
If person B takes X hours to do the whole job, their rate is 1 over X, job per hour.
Okay, 1x.
Since A takes 6 hours less, their time is X minus 6 hours.
Uh-huh.
So A's rate is 1 over by 6.
Got it.
When they work together, you just add their rates.
And that equals their combined rate. Now, the combined time is 13 hours, 20 minutes. We need that in hours, right?
Yeah, need consistent units. 20 minutes is 20/60. That's 13 of an hour.
So 13 and 13 hours as a fraction.
That's 39 plus 1 over 3, 4 over 3 hours.
Okay, 403 hours for the combined time.
So the combined rate is the reciprocal of that, 1 over 403, which is 340.
Ah, right. So the equation is A's rate plus B's rate equals combined rate.
Exactly. Frac 1x plus frac 1x, straight down.
And there we have x in the denominators again. Looks like another quadratic incoming.
Yep, solving this. Common denominator, combine, cross, multiply. It's a bit of algebra.
League, sir.
It leads to 3 by 2 98x's plus 240 equals $.
Okay, 3 by 2 98x's plus 240 equals dollars of. Does that factor nicely?
It does, actually. It factors into 6 by 30, 3 by 8 equals $1.
So, two possibilities again. X or X equals 83.
Right. Now we think about the context. X is B's time.
Uh-huh.
If B's time X was 83 hours, which is 2 and 23 hours.
Then A's time would be by 6, so 83 minus 6, that's negative.
Exactly. Negative time makes no sense here. So we have to discard the 83 solution.
Which leaves X equals 30.
So person B takes 30 hours to do the job alone, and person A takes 36 equals 24 hours.
Makes sense. Again, it's the algebra plus the logic of the situation.
Yeah.
And it seems exercise 6a has more of these work rate problems too.
It does. They show how quadratics model situations where rates combine, and the outcome isn't just a simple linear sum.
Let's move on to geometry. Always like geometry.
Me too. Visual.
Here's a classic. Right triangle. Hypotenuse is 13 centimeters.
Okay, 13.
The other two sides, the legs, their lengths differ by 7 centimeters.
Ah, okay. Difference is 7.
How do we find the lengths of those two unknown sides?
Well, right triangle immediately screams.
Pythagorean theorem. $2 plus B2 will C2 too.
Exactly. Let's call the shorter leg X centimeters. Since they differ by 7, the longer leg must be X plus 7 centimeters.
Right.
And the hypotenuse C is 13. So plug them in. $6 plus X plus 7.
BQ.
Equals 132 too.
And look, the squares in Pythagoras directly give us the 6 by L's. It's quadratic from the start.
Precisely.
Okay, so we expand 6 by x plus 7 $2. That's 6 by L's plus 14x plus $14 $9. And 132 2 is $169.
Right. So the equation is 6 by dollars plus 14x plus 14 by 120 equals our year.
Combine the $6 move the 169 over.
You get 2 by a few dollars plus 14 by 120 equals.
Can we simplify that? Looks like everything is divisible by 2.
Good catch. Divide by 2 and it becomes 6 by the others plus 7 by 60 equals much nicer.
Does it factor, factors of negative 60 that add to 7, 12, and -5.
Yep, so it factors into 6 plus 12 by 5 equals many dollars.
Giving possible solutions x and equal 12 and x equals 5.
Again, context. X is the length of a side.
Can't be negative.
Exactly. Discard negative 12, so x must be 5.
Which means the shorter side is 5 centimeters.
And the longer side is x plus 7, so 5 plus 7.
12 centimeters.
So the sides are 5 centimeters and 12 centimeters, and we can check. $52 plus 122 equals 25, plus 144 equals 169.90, which is $132.
Yeah.
It works.
It's really cool how that fundamental geometry rule leads straight to a solvable quadratic. Okay, another geometry one. A rectangular veranda.
Okay.
The length is 3 meters more than its breadth.
Length breadth plus 3. Got it.
And here's the twist. The numerical value of its area is equal to the numerical value of its perimeter.
Area equals perimeter. Interesting condition.
What are the dimensions?
All right, let's define things. Let the breadth be x meters.
And pay breadth x.
Then the length is x plus 3 meters.
Right.
Now, area is length times breadth. So area is 6x plus $3.
And perimeter is 2 times length plus breadth.
Yep. Perimeter $2, x plus 3 plus x equals 2x plus 3.
Which is $4 plus 66.
Okay. The problem says area equals perimeter numerically.
So 6 plus 3 is 4x plus 66.
Let's expand the left side. 6 by dollars plus 3x is 4x plus 6.
And rearrange into standard quadratic form, move the 4x and 6 over.
We get 6 by 2 by 6
6 by 6, this was other dollars. Factors of negative 6 that add to minus 1. Minus 3 and plus 2.
Perfect. 6 by 3x plus 2 equals $1.
So possible values for x are 3 and minus 2.
And x is the breadth.
Can't be negative. Discard minus 2.
So the breadth x must be 3 meters.
And the length is x plus 3, so 3 plus 3 equals 6 meters.
Dimensions are 3 meters by 6 meters. Let's check. Area 3, 6 equals 18. Perimeter equals 2. 3 plus 6 equals 2. 9 equals 18. They match.
Fantastic. And looking at exercise 6b in the guide, it's packed with geometry problems. Areas, sides, squares, paths, flower beds, rooms.
Yeah, it really drives home how often quadratics come up when you're dealing with shapes, especially anything involving area calculations or the Pythagorean theorem, because those inherently involve multiplying dimensions or squaring them.
Right. Anytime you multiply unknowns or square them, a quadratic might be lurking. Okay, let's switch focus again. Distance, speed, and time problems.
The Tyriel-Della stuff.
Here's a common type. Increasing a car's speed by 10 kilometers per hour reduces the time for a 72-kilometer journey by 36 minutes.
Okay. Faster speed, less time. Makes sense.
What was the original speed?
Okay, let's use the relationship time, distance, speed.
Right.
Let the original speed be x kilometer per hour.
Okay.
The original time to cover 72 kilometers is 72 divided by x hours. So $2 is 72 b corso. The new speed is x plus 10 kilometers r. The new time for the same 72 kilometers is 72 divided by x plus 10 hours. So $2 because 72, x plus 10.
Okay, $2 and $2 too. The problem says the time is reduced by 36 minutes.
Meaning the original time, $T minus the new time, $2 equals the time saved.
Which is 36 minutes. We need that in hours, though.
Right, consistency. 36 minutes is 3,660 hours. Divide by 12, 35 hours. Or 0.6 hours.
Okay, 0.6 hours. So the equation is original time, new time, time saved.
Exactly. Frac x plus 10 equals 0.6s.
And they're the unknowns in the denominator again. Looks quadratic.
Definitely. To solve this, you'd multiply everything by the common denominator, which is 6x plus $10 to clear the fractions. That gives $72 x plus 10. 72x equals 0.6x plus 10.
Simplify the left side. 72 because it's plus 720. 72 by 9, just 720.
Right. So $720 at 0.6x plus $10. Let's expand the right side. 722 by 2 plus 6 by low.
Dealing with the 0.6? Maybe divide the whole equation by 0.6?
Good idea. 720 divided by 0.6 is $1,200.
Okay. And $2, 6 by $2 is 6 by $2, and 6 by 6 is 10 by low.
So $1,200 plus 10 by dollars.
Rearranged to standard form, 6 by dollars plus 10 by 1,200.
Okay, 6 by dollars plus 10 by 1,200. We need to factor this. Factors of net of 1,200 that add to 10. Maybe think 30 and 40.
Yeah, plus 40 and another 30 would work. 40 times another 30 equals 1,200, and 40 plus another 30 is 10,000.
Perfect. So x plus 40 by 30 by 30.
Which gives possible solutions. X, I mean, at 40 and X was 30.
And x represents speed.
Can't be negative. Discard negative 40.
Leaving x, the original speed was 30 kilometers.
New speed, and you roll 700 and 240 equals 1.8 hours. Difference between 2.4, 1.8.6 hours.
And 0.6 hours is 36 minutes. Checks out perfectly.
Great. It really shows how that inverse relationship between speed and time leads to these quadratics. Here's another car one about fuel efficiency.
Okay.
Car A travels X kilometers per liter. Car B is more efficient. It travels X plus 5 kilometers per liter.
Got it. B goes further on a liter.
They both travel 400 kilometers. Car A uses 4 liters more petrol than car B for this journey.
Okay, A uses more fuel. Makes sense. It's less efficient.
The question asks, how many liters did car B use?
Okay, first step is to figure out the liters used by each car in terms of X.
Right, liters is since kilometers per liter.
Exactly. So for car A, liters used 400x.
And for car B, liters used is 400x plus 5.
Okay. Now the problem says A used 4 liters more than B.
So liters for A, liters for B, 4.
Which translates to frac 400x plus 5.
It's very similar in structure to the last problem.
It really does. Same process to solve it. Clear the denominators by multiplying by 6 plus $5.
Okay, that gives $400, x plus 5. 400x is 400x plus 5.
Simplify the left side. 400x plus 2,000, 400 by, just $2,000.
So $2,000, 4x, x plus 5. Expand the right. $2,000, 4 by 2 plus 20 by bar.
We can simplify this by dividing everything by 4.
$2,000 for OX, $500. 4 by 2 for 4, OX by 2, 2. 20 by 4 is 5 by I.
So $500 plus 5 by $2 plus 5 by 2 plus 5 by 500.
6 by $, plus 5 by 500 plus 5 by 500 will be a grand.
6 by $2 plus 5 by 500, sum of 500. Sum is plus 5. Yes.
So 6x plus 25 by 20 is all.
The giving potential solutions, x and 25 and x equal 20.
X is kilometers per liter. Fuel efficiency can't be negative.
Discard negative 225, so x doing.
Okay, so car A gets 20 kilometer liter. Car B gets x plus 5, which is 25 kilometer liter.
Right. But what was the question again?
How many liters did car B use for the 400 kilometer journey?
Okay. Car B's usage was 400, x plus 5.
So 425.
This is 16. Car B used 16 liters.
Got it. And again, exercise 6C seems to have more variations, trains, planes, different speeds.
Yeah, it really hammers home how useful quadratics are for anything involving rates like speed and how they relate inversely to time or directly to consumption over a fixed distance.
Okay, let's move into the world of commerce. Cost price, selling price.
Money math.
Here's one. A trader sells an item for 24 rupees.
Okay, selling price 24.
By doing this, they make a percentage loss that is numerically equal to the cost price.
Ooh, that's a classic setup. Loss percentage equals cost price number.
What was the cost price?
Okay, let the cost price be X rupees.
CPX.
The percentage loss is also X percent.
Loss X percent.
Now, the actual amount of loss is X percent of the cost price.
So by 100 times X.
Which is 6 by 2, $100. That's the loss amount in rupees.
Okay. And we know that selling price, cost price, loss amount.
Exactly. So $24 X frac 2.
And there's our 62 term. It's quadratic.
Yep. To solve it, maybe first get rid of the fraction. Multiply the whole equation by 100.
Okay. $2,400 equals 100x by 22.
Now rearrange into standard form. Let's move everything to the left side to make 6 by 22 positive.
6 by $2 plus 2,400 plus 2,400.
You get $200x plus 2,400 equals the law.
Factoring this, need factors of 2,400 that add up to 2,400. Think about 24 and 100. Maybe 60 and 40.
Let's see. Not negative 60, not negative 40. Product is 9 negative 60. 2,400 sum is 9 negative 60 plus 9 negative 40, 9 negative 100.
Yes.
Perfect. So 6 by 60 by 40 equals 11 here.
Which gives two possible values for x, 60, and 40.
And both are positive, so potentially valid cost prices. This is interesting.
Wait, how can there be two cost prices?
Let's check each one. If the cost price X was 60 rupees,
the loss percentage is also 60%?
the loss amount is 60% of 60, which is 0.666 is 36 rupees.
Selling price equals cost price loss equals 60/36 equals 24 rupees. That works.
Now, what if the cost price X was 40 rupees?
Then the loss percentage is 40%.
The loss amount is 40% of 40, which is 0.440 equals 16 rupees.
Selling price, cost price loss equals 40/16 equals 24 rupees. That works too.
So in this specific scenario, there are two possible original cost prices, 40 rupees or 60 rupees, that both satisfy the condition of selling for 24 rupees with the percentage loss equal to the cost price.
That's really fascinating. A quadratic giving two genuinely valid answers in the context of the problem.
It happens sometime. It highlights that you always need to interpret the mathematical solutions back in the real-world context.
Yeah.
And exercise 6C apparently has more of these business-type problems, profit, gain percentages.
Yeah, showing how quadratics pop up when percentages relate back to the unknown base value.
Exactly.
Okay, finally, let's look at a few miscellaneous problems that show even more applications.
All right, the good grab bag.
Here's one using a known formula. The sum S of the first n natural numbers is zeroed off, frac 1, 2, n, m plus $1.
The sum formula.
If the sum S is 276, what is the value of n?
Okay, so we have the formula and the sum. We just need to solve for n.
The equation is $276, frac 1, 2, n, m plus $1.
First step, maybe multiply by 2 to clear the fraction.
$2, 276 per pound is 505 to 2. So $552 plus $1 plus $1.
Expand the right side. 552 equals N2 plus $1.
Rearrange into standard form. $2 plus N552 equals $1.
Okay, $2 plus N552 equals your dollar. Need to factor this. 552 is kind of large. Need factors that differ by 1. Maybe think about square roots. Square root of 552 is around 23 something.
Let's try 23 and 24. $23 and 24, 2 plus 4 equals 460 plus 92 plus 92 equals 552, $2.
Nice. So we need factors that multiply to negative 552 and add to plus 1. That would be plus 24 and negative 23.
Right. So 1n plus 24 and 23 equals $1.
Giving potential solutions n that equals 24 and n equals 23.
N is the number of natural numbers being added. It has to be positive.
Correct. Discard negative 24, so NA is 23.
The sum of the first 23 natural numbers is 276.
Another neat application. Here's a riddle-like one. A 2-digit number.
Okay.
The product of its digits is 6.
Product X.
If you add 9 to the number, the digits reverse their places.
Add 9, digits swap. What's the number?
Okay, let's represent the number. A 2-digit number is $10 times text units.
It's called the tens digit X and the units digit Y. So the number is $10 plus YY.
Good. First condition. Product of digits is 6.
Here, 6 times Y equals 6.
Equation 1.
Second condition, add 9, digits reverse. The reverse number would be $10 plus Y plus Y plus 9 plus 90 plus X Y.
Equation 2.
Let's simplify equation 2. Get all the X's and Y's together. Maybe move X to the right and 10Y to the left.
Or maybe move X and Y to the right. $9? 10Y plus by 10, $9, $9.
Okay. $9, 9Y, 9 by R's.
Okay, $9 and 9 by adder.
Divide everything by 9.
$1 YXC, or Y equals X plus $1. That looks simpler. Yeah, E equals X plus 1. Now we have a system of 2 equations. 6 I's and dollars are hours and 6 I's X plus 1.
We can substitute the second into the first. Replace Y and 66 sixes with 6 plus 1.
Good idea. That gives 6X plus 1 equals 6 to 5.
Expand. 6 by dollars plus X was 6 by 5, 6.
Rearrange. 6 by 6 plus the Dales. 8. A quadratic again.
And this one factors easily. We saw it before, kind of. Factors of 9x6 that add to 1 plus 3 and an F to 2.
Right. 6 plus 3 by 2 equals $2.
So possible values for X, the tens digit, are -3 and 2.
A digit in a positive number can't be negative.
Discard -3, so X2.
If X2, then YX plus 1, well, 2 plus 1 equals 3.
So the tens digit is 2, the units digit is 3, the number is 23.
Let's check. A product of digits 2, 3 equals 6. Yep. Add 9 to 23 gives 32. Are the digits reversed?
Yes.
It works. Cool.
It is cool. And there are more in the miscellaneous section too. Age problems, boats and streams, pricing cloth, buying books, planning picnics.
It really shows the incredible range. Anytime you have relationships that involve squares, products of unknowns, or inverse relationships like speed time or rate time, a quadratic equation might just be the key to unlocking the solution.
So wrapping this all up, it's really clear that quadratic equations aren't just some abstract math thing.
Not at all.
They are genuinely a versatile and powerful tool. They help us tackle such a wide array of practical problems.
That's the key takeaway, I think.
Whether it's figuring out numbers or work in time or geometry or speed or even buying and selling.
Yeah, they provide a structure, a mathematical model for understanding these situations.
By learning how to translate the words into the equation and then using the algebra to solve it, you really do get a deeper insight, don't you, into how these different quantities are connected.
You absolutely do. It goes beyond just seeing the surface numbers. You start to grasp the underlying dynamics, the relationships between them. It's a shortcut to being, well, better informed about how things work quantitatively.
It's like having a secret code almost to understand the world a bit better mathematically.
That's a nice way to put it.
So a final thought for you listening. Think about other everyday situations, maybe something at work or planning something at home, where you have unknown amounts or quantities that are linked together by certain rules or conditions.
Yeah, where things aren't just simple addition or subtraction.
Could a quadratic equation be hiding there, lurking beneath the surface, just waiting to reveal a hidden answer?
It's definitely worth keeping an eye out for those squared relationships or inverse proportions. You might be surprised where they pop up.
Definitely something to think about. Thanks for taking this deep dive with us today.